talk about the issue of selecting probability distributions for risk quantification in projects, the most popular question ever is, without doubt, what is the best distribution, the triangular or the Pert, also called beta Pert? The enormous popularity of the triangular can be attributed to the fact that for many years it was the only recommendation suggested in PMI's PMBOK. Any professional certified as PMP has studied about triangular by using it as a useful, convenient, and easy method to incorporate the expert's criteria by defining its three parameters: a minimum value, a most likely or modal value, and a maximum value. More recent versions of the PMBOK already include the alternative mention of the Pert, but the triangular one gains popularity for many years of a monopoly as a recommended distribution in the absence of sample data. In the example of a construction of a residence, 8 standard risks have been identified. That is, risks where, if they were to occur with a certain probability of occurrence, an impact of a certain magnitude would be generated, either as a variation in the schedule or in cost. In risk 7, unknown site conditions, a variability of up to 95% the most probable value is allowed as a minimum point. That is, with respect to the modal value, a reduction of up to 5% in the scheduled time or in the cost would be expected as a minimum point. With a maximum value of 200, this implies that, with respect to the most probable value, the scheduled time or cost could be up to twice that value. As seen, there's a great asymmetry in the shape of the curve. There's much less variation towards the side of saving time and costs, towards the left side or minimum side, than there is towards the side of the extensions in time and costs, towards the maximum or right side. Any experienced project manager knows that this is almost always the case. You are more likely to be late than to get ahead of your tasks. You are more likely to go over budget than to underestimate the value of your budget in reality. See the Pert curve that using these three parameters could be created for this risk. The top of the curve is 100%, the most likely value. The 80th percentile, that is the point at which 80% of probable events accumulate, reaches 129%. That is, in terms of schedule or cost, there's a 20% probability that the time of tasks impacted by this risk or their budgeted cost is greater than the respective 129% of the time of modal amount. Notice what happens if we use exactly these same parameters, 95% of the mode as a minimum and 200% of the mode as a maximum, but this time with the triangular distribution. The cusp of the curve is still 100%, the most probable value. The 80th percentile, that is the point at which 80% of probable events accumulate, reaches 154%. That is, in terms of schedule or cost, there's a 20% probability that the time of tasks impacted by this risk or their budgeted cost is greater than the respective 154% of the time or modal amount. Better still is to compare both distributions. Using exactly the same three parameters of minimum, mode, and maximum, the triangular shows a much more conservative scenario. That is, at the level at which Pert maintains 20% of its results above a level of 129%, that is the 80th percentile, the triangular one leaves almost 50% at that level. That is, the area under the curve of probability results greater than 129% is 20% versus 49%. That is why we affirm that the triangular is more skewed, and therefore it will tend to have tails that are fatter than the Pert, towards the side where the asymmetry is, as both are asymmetric curves to the right. That is, the right side of both curves carries more probability than the left side. The triangular one will always tend to carry more probability towards the side of asymmetry. That is, in this case, to the right side. In this example, the Pert distribution has a skewness or asymmetry coefficient of 1, while the triangular one has a coefficient of 0.56. So far, however, we have not measured the final impact that the choice of one distribution or another has on the results of the project. Let us use saffron risk to measure such impacts over the activities and the overall project. In saffron risk, one first defines the activities on a Gantt type schedule, either by creating it from scratch or by importing it from Primavera, P6, or MS Project. On the other hand, the risks are defined. As we have seen in this example, there will be 8 standard risks, and we will continue to use risk 7, unknown site conditions, for our example. Having previously defined both elements, tasks or activities, and risks, we now proceed to cross over which risks impact which tasks in 2 different dimensions: the duration of the activity and the impact on cost. For example, look at activity 19, basement walls construction, which has a deterministic duration of 13 days. In the Risk Mapping tab, you can observe that 3 standard risks impact the duration and cost of this task: worker accidents and injuries, poorly written contracts, and unknown site conditions. With the independent interaction of these 3 risks, Saffron automatically builds the duration of this task, showing the dynamic histogram with a minimum of 11 days to a maximum of 22 days. Remember that the unknown site conditions risk is highly asymmetric. It could even double the most likely value in terms of duration and cost. Let's now run a simulation using Pert distributions for all 8 standard risks that impact the duration and cost of project activities. After simulating activity 19, basement walls construction would look like this, assuming Pert distributions. Indeed, the expected value would be 13 days, with a 53% probability of reaching such objective in duration. The 80th percentile would be greater than 14 days, which is 14% longer than expected. This would mean adding just over a contingency day to satisfy an 80% confidence level. In very extreme conditions, however, a maximum of more than 28 days could be reached, perhaps when extreme conditions occur simultaneously with the impact of the 3 risks that affect this activity. Let's send the duration graph of this task to graph comparison to later compare it against the results of an alternative triangular distribution. We rename this scenario with the name Pert. Now we simulate again, but assuming triangular distributions for all the 8 standard risks that have been previously defined. Note that we can implement this in the Analyze tab by using the pre- and post-mitigation functionality that allows us to evaluate any combination of alternative scenarios. In this case, we apply all Pert-type distributions in the pre-mitigation scenario and all triangular distributions in the post-mitigation scenario. Previously, for each of the risks, such as in this case unknown site conditions, we have added duration and cost impacts with Pert distributions in the pre-scenario and duration and cost impacts with triangular distributions in the post-scenario. After the respective simulation, we obtain the following results. Under these new assumptions, the probability of meeting the deterministic time drops from 53% to 50%, which is not very significant. However, the 80th percentile happens to be more than 16 days compared to 14 days under the Pert assumption. This is a 25% contingency with respect to the 13-day expected value, compared to the 14% contingency if the assumption of a Pert distribution had been used. While under Pert assumptions, the maximum could be 24 days, under the triangular assumptions, the maximum could exceed 31 days. By submitting this graph through the Send to Comparison option, we get the following. Here, it becomes easy to compare the cumulative lines under both assumptions and assess, at P80, how much increase in time contingency would have to be included if the assumption of triangular distributions were used. So far, we have seen how, by assuming triangular distributions, we're being more conservative in assigning higher contingency levels under the same 80% confidence level. Now, let's look at what happens in the project in general. Under the assumption of triangular distributions, the 80th percentile for the duration of the entire project amounts to 252 days. This is almost 40 days more than its expected value. This is a 19% increase. In this scenario, there's only a 2% chance of finishing the project before the deterministic duration of 212 days. Now, let's see the simulated results using Pert distributions, which we can access by simulating under pre-mitigation conditions. Under the assumption of Pert distributions, the 80th percentile for the duration of the entire project amounts to 246 days. This is 33 days more than its expected value, a 16% increase. In this scenario, there's a 1% probability of finishing the project before the deterministic duration of 212 days. By sending this curve through the center comparison functionality, we can compare both assumptions. Here, at the P80 level, we observe 6 additional days of contingency required under a triangular. This is only 2.4% more in the magnitude of such a time contingency. In other words, the final impact on the total project has not been as great as we would have expected, given the difference in the 80th percentiles of the 8 risks considered. Look at the following table. In a simple average, the P80s of all the triangular distributions for the 8 risks are 12% higher than the respective P80s of the Pert distributions. As we saw in the unknown site conditions risk example, the triangular P80 is 20% higher than the Pert P80. That is, while the triangular P80 reaches a level of 154% with respect to the model value, the Pert P80 barely reaches 129%. How is it then possible that the impact on contingencies, triangular or Pert, is reduced to only a difference of 2.4% valued at the 80th percentile level? The answer has to do with the combinatorial analysis of a Monte Carlo simulation and the theory of conditional probabilities. With the thousands or tens of thousands of iterations that are generated in a simulation, only in very few cases would high values be simultaneously generated in both one risk and any other in the same iteration. And that is so because we're doing an analysis on a value that is already extreme, which is the 80th percentile. By definition, the probability that a certain value is exceeded in a certain activity at the 80th percentile is 20%. If you have 2 activities, the probability of exceeding both simultaneously is not 28%, rather 4%, 0.2 to the second power, 0.04. Since the conditional probabilities are not added or averaged, but rather multiply when there's conditionality or simultaneity. For this reason, when we compare at the level of an activity, seeing its differences in details between one alternative distribution and another, Pert and triangular, somewhat significant differences could be observed. When we start to add more distributions where some depend in sequence of the others, that is, a project, as a sequential series of dependent and simultaneous tasks, and we evaluate a non-central value, such as an 80th percentile, the differences between one distribution and another tend to become less significant due to the compound or power effect that exists in the tails of the distributions. The triangular distribution then has these desirable characteristics. 1, it is relatively easy to specify. And 2, even if you overestimate the extremes, not significantly at least, it can be considered a conservative distribution. The triangular will tend to have tails that are fatter than the Pert ones. The analyst should decide which distribution best describes the behavior of the tail. The triangular distribution has these shortcomings. 1, in cases where there's a small possibility of an extreme event, the triangular will tend to overestimate the probability of an extreme result in this case. And 2, triangular assumes the linearity of the probability density function. We tend to prefer the shape of a Pert distribution which assumes that the predominance of the results occur in the most probable range, and then the tails are rounded. In other words, the triangular distribution creates a mathematical discontinuity at its maximum point or mode, something that the Pert avoids. We can then conclude that there's a certain impact of differentiation between the use of Pert and triangular distributions if the analysis is done at the individual level of activity. As we add more risks and we see the image from a perspective of the sum of all the tasks in a project, the differences that may exist between one assumption and the other continue to appear, but will not be as significant as when they were seen with greater specificity at the level of each activity. Seeing the entire forest from a broader perspective prevents us from seeing the detail of what is happening at the level of each activity. In other words, there will be some differences between the use of Pert and triangular in a project. But in the end, the impact may not be as significant as it would be at the level of each of the activities in the absence of correlations. If we were doing this analysis on the averages, there would be arithmetic consistency between the risk variations and the differences between Pert and triangular distributions. And that is so because our model has no correlation between risks yet. If correlations were present, the results could even be more or less counterintuitive than they appear to be. We will see the subject of correlations in a later installment.